For the second lecture of Chapter 5, we're going to be talking about the enthalpy of a reaction. Recall that the enthalpy is simply the heat component of the reaction, how much heat the reaction releases. We previously talked about work, but what we'll say is that we're going to drop work and simply talk about heat. So we can actually define the change in enthalpy as delta H. Really, the change in anything is the delta of that anything. And again, the change in simply is products minus, or final minus initial. We're used to it being final minus initial. And because the final, in our case, are products, the initial are reactants, we can actually say it is the heat of the products minus the heat of the reactants. So an example for here, so if we take this gas and react it with oxygen, this is a combustion reaction, a bunch of heat is released. So what we can say is we can say that the reaction releases a certain amount of heat, and we can actually measure that certain amount of heat. In this case, it's going to be negative 890 kilojoules. So we'll be studying this exchange between the reactants and the products, this delta H, which occurs here. So it's also called heat of reaction, enthalpy of reaction, or heat of reaction, because enthalpy really and heat are the same thing. So kind of like we talked about delta E, we can say the same thing about delta H. If heat is absorbed by the reaction, by the system, from the surroundings, then the delta H will be positive. That's because the change in the system in terms of heat is positive. The system gains heat. We'll call this endothermic. Previously we called it endergonic, and endergonic just simply meant both heat and work in general energy. Heat here we're only talking about the heat component, so endothermic. And then if heat is released, we'll call it exothermic, and the delta H in this case would be negative. Negative because heat was released by the system, so the system's heat went down, is the idea. And then another way of saying it is that the delta H is less than 0. That's another way of saying it's negative. Or delta H is greater than 0. Another way of saying it is positive. So here is how we indicate heat in chemical reactions. There's really two ways, and one of these is the more common way. The first, less common way, is we write the chemical equation, balanced chemical equation. Notice we have it balanced. And then we write heat on the product side if heat is released. If heat were absorbed, we would actually put it on the reactant side, on this side. But this much heat is released, and we indicate that as we'll pretend that heat is actually a product. The more common way of writing heat in chemical reactions is by actually, at the end, indicating the delta H of the reaction. In this case, the delta H is negative 483.6 kilojoules. And we indicate that heat has been released by the little negative sign here. So this reaction is exothermic because heat, delta H, is negative. And again, this is, if you take a look at the reaction, if you're aware of it, here we have hydrogen reacting with oxygen to produce water. And this is a pretty explosive reaction. Hopefully you had the pleasure of seeing this performed by your previous chemistry teacher. If not, we can accommodate that. So we can ask then a question, much like we asked about chemical amounts with heat. So this is actually a, you've guessed it, stoichiometry problem. So stoichiometry is back. Actually, stoichiometry never left. So we got some stoichiometry. So stoichiometry is back, tell a friend, and we're actually going to do some stoichiometry with this problem. Okay, so the problem involves, let's go back real quick and take a look at the problem in detail. So looks like we have ourselves a chemical equation with a bunch of heat released. This is new. And the question is, if I burn, or if I react, 4.5 grams of methane, this substance here is methane, how much heat is released? Now, based on the equation, it actually says that if I have 1 mole of methane burning, then I release 890 kilojoules of heat. If I have less than a mole, which we'll see 4.5 grams is actually less than a mole, then obviously I'll have less heat released, but we want to know exactly how much heat is released. when I burn that much methane. Okay, so let's get to it. Looks like we'll have to set up a little stoichiometry problem. So we'll begin, as we usually do, with the amount given. So 4.50 grams of methane, which is CH4 in this case. And we'll have to first convert from grams of methane to moles of methane. And then from moles of methane, we'll have to convert to kilojoules. And that's if you take a look at the previous example. Because the moles of methane is actually related to the heat. It's 1 mole of methane produces this much heat. So after we convert to moles of methane, the second step will be to convert to heat. So let's go ahead and convert from grams to moles. This first step is simply from grams to moles. Anytime we go from grams to moles, it is 1 mole we are reacting, and the grams comes from the periodic table. And in this case we have carbon, which is 1201 grams. We have hydrogen, which is 1.01. We got 4 of them. So if we multiply this portion times 4 and add it all together, we should get ourselves 16.05 grams. And that's what goes in here. 16.05 grams of in methane. So grams of methane's out, and then based on the chemical equation, we know that 1 mole of methane, we can actually put methane here as well. It's a good idea to label your units along with the chemical that you're talking about. We know that 1 mole of methane actually releases exactly 890 kilojoules. So we'll leave this negative in there just to indicate that we are being released. Heat is being released. So we'll do negative 890 kilojoules in the second section. So what's left to do essentially is multiply across the top here. So we'll do 4.50 times 1 divided by 16.05 multiplied by negative 890. Giving us a total of negative 249.5 kilojoules. And because we've got 3 significant figures to begin with, let's go ahead and end up with 3 sig figs, which gives us negative 250, because the 5 rounds the 9 up. And don't forget the decimal place to include that 0 as a significant value. Negative 250 kilojoules is how much heat is released, which is quite a bit of heat. Released. Negative 250,000 joules of heat released when you burn 4.5 grams of methane, which really isn't that much methane, 4.5 grams. 4.5 paper clips worth of methane. Okay, let's say a few more words about enthalpy. Enthalpy is an extensive property, and if you recall, extensive means that it depends on how much you have. So mass, for example, is an extensive property, because 2 pieces of matter, if their mass is different, then if their amounts are different, then their mass will be different. An intensive property, recall, is something like density is an intensive property. So, because if you have a small chunk of some sort of metal and a big chunk of that same metal, the densities of the two will be the same, because density is an intensive, it's what's inside, but the mass will be different, and the energy of these two will be different. This one will have more energy stored inside of it, which makes sense. That's why enthalpy, we say, is an extensive property. And we can also say that delta H, the change in heat, is equal in magnitude but opposite in sign for the reverse reaction. So what we can do, this is the reaction we just worked with, we can flip this reaction around. We saw methane as a reactant and oxygen as a reactant, and these are the products. We can flip the reaction. This is more of a theoretical flipping, but many reactions can be reversed. So this is actually correct, and what we'll end up doing is essentially changing the negative to a positive. So anytime you flip an equation, your sign changes. The enthalpy also depends on the state of the reactants and products. So for example, if you want to make liquid water into gaseous water, the liquid molecules will have to speed up to become gas, so energy will have to be absorbed by the system. And we can calculate exactly how much energy is absorbed. In this case, 88 kilojoules of energy is required to make liquid water into gaseous water. So take a look at state symbols. In other words, they're important. If one reaction says you're producing liquid, another says you're producing gas, their delta H's will be different, is the idea. And actually we're going to finish up, looks like, with this problem here. It's very similar to the previous problem involving some more stoichiometry. So the reaction here is the reaction of magnesium with oxygen. You'll actually have the pleasure of the opportunity to perform this reaction in lab, in one of our labs coming up. But anytime you burn magnesium in oxygen, you form magnesium oxide as predicted, but an enormous amount of heat is actually released. If you've ever seen magnesium burn, it produces a very bright white light and a great deal of heat at that. Really actually this much heat, quite a bit more than the methane burning as we saw previously. So the question is this: how many kilojoules of heat are absorbed when 7.50 grams of magnesium oxide are decomposed into magnesium and oxygen? So what we're doing here, first of all, the reaction is not written as a decomposition, it's written as a synthesis. So what we're asking here in the problem is what's the reverse of this reaction. So let's go ahead and attempt this. So first of all, let's go ahead and write the reaction in the reverse order. So we're simply flipping the products and reactants, and we got ourselves magnesium oxide decomposing into magnesium and oxygen gas. And to balance the equation, we'll put a 2 here and a 2 here. Our delta H for this reaction then is simply the opposite sign of the previous one. The previous one was negative 1204, so we'll make it positive 1204 kilojoules is the idea. And now we begin with 7.50 grams of MgO, 7.50 grams of magnesium oxide, and we're asked for the heat to find out how much heat this would release. Again, we'll follow a similar pattern to what we've done previously. We'll have to first convert from grams of MgO to moles of MgO, and then from moles of MgO to heat. Because if you take a look at the balanced equation, 2 moles of MgO produce this much heat, and that will be our relationship there. So first, let's go from grams to moles. So grams of MgO here, and 1 mole of MgO. If we take a look at the periodic table, we'll find that the total mass of magnesium and oxygen, magnesium is about 24, oxygen is about 16, should be about 40, and 40.30 to be exact. And then once we've done that, let's go ahead and convert from moles of MgO to kilojoules, which in this case, you have to be careful here, 2 moles of MgO produce 1204, positive 1204 kilojoules. So again, the balanced equation has to be consulted. You have to make sure you put this 2 here. If you do not, you'll get the answer wrong, because the relationship is 2 moles producing this much heat. And then essentially we'll be asked to simply calculate this out. So let's go ahead and do 750 divided by 40.30 multiplied by 1204 divided by 2. And we should get ourselves, the final answer should be about 112 kilojoules. And that is a positive value, just to reiterate. And it's positive because we're decomposing, just like the reaction shows, and in order to decompose this requires an input of heat into the system. So we'll show it with a positive. Usually you don't have to include the positive, but in this case, just to reiterate, that it is a positive change. Okay, and that's it for this second lesson of Chapter 5. We'll see you here next time.